Why does stacking champagne glasses and pouring from the top create a perfect cascading fountain instead of a catastrophic, expensive mess? A champagne fountain isn't magic. It's gravity doing exactly what gravity always does, pulling liquid downward through a carefully arranged stack of glasses, one overflow at a time, in perfect physical sequence. Each glass has a finite volume. Once liquid reaches the rim, surface tension loses the battle against gravity, and the overflow spills into the next tier below, triggering an automatic chain reaction through every level. Picture a rooftop soiree in Monaco. Max Gold, barefoot on white marble, silk robe open, gold chains gleaming, positions himself before a 16-glass pyramid worth more in champagne than most people's monthly rent. Before a single drop is poured, the pyramid must be stable. Each glass rests on the rims of two glasses below, distributing its weight outward and downward, the same load-spreading logic built into Roman stone arches. A classic four-tier fountain uses around 30 glasses, 4 on the base, 3 above, then 2, then 1 at the apex. That triangular geometry ensures every upper glass has exactly 2 lower glasses ready to catch its overflow. Here's where most first-time fountain builders go wrong. They assume any pour rate works because gravity handles everything. That assumption ignores kinetic energy, and kinetic energy doesn't care about your party timeline. Kinetic energy scales quadratically with speed. Double your pour rate, and you quadruple the energy hitting the top glass. That energy translates directly into turbulence, splash, and foam that bypasses the cascade entirely. Champagne is carbonated. Aggressive pouring agitates dissolved carbon dioxide, triggering rapid bubble formation. Foam expands volume unpredictably. The top glass overflows before it should, collapsing the timing of the entire cascade. So, the real physics battle inside a champagne fountain isn't simply gravity versus the glass. It's gravity versus surface tension, versus kinetic energy, versus dissolved gas, all happening simultaneously at every tier. The solution is a controlled, steady pour angled along the inside wall of the top glass. This minimizes agitation, preserves carbonation, and lets gravity, not turbulence, dictate when and where the overflow begins. Once the top glass reaches capacity, overflow isn't random, it's deterministic. A standard champagne flute holds roughly 150 milliliters, so a practiced host knows exactly when the cascade will begin. As the top glass overflows, liquid fans outward and downward into 2 second-tier glasses simultaneously. Each of those fills overflows into 2 more, and the cascade propagates geometrically, doubling its reach with every tier. Gravity provides constant downward pressure proportional to the depth of liquid, not the height above each glass. Taller stacks generate more pressure at the base, which is why a 6-tier fountain fills its bottom row faster than a 2-tier version. But here's where it gets harder. Every additional tier multiplies the structural load on the base glasses. A 6-tier pyramid places the weight of 21 glasses plus liquid on that bottom row, and glass is not forgiving. Stability here borrows from moment of inertia, the resistance of a system to rotational disruption. A wider base distributes mass farther from the center, dramatically resisting the toppling force of any lateral bump. Remember that quadratic kinetic energy scaling. It surprises even physics enthusiasts. Most people expect energy to double when speed doubles, but it quadruples. That gap between intuition and reality has ruined many expensive fountains. Here's a subtle gravity effect, hiding inside every tier. Liquid sitting in a partially filled glass exerts hydrostatic pressure on its own base. Pressure that increases with depth. That pressure accelerates the overflow stream as it drops to the next tier, making each cascade slightly faster than the one above it. That acceleration compounds across every tier. By the time champagne reaches the base row, gravity has accelerated it repeatedly, each drop arriving with more kinetic energy than the one that triggered it. The fountain isn't just flowing, it's gaining momentum as it descends. When every variable is controlled, pour rate, glass alignment, base stability, the result is a self-sustaining liquid machine. Champagne flows continuously downward, every glass filling in sequence, the whole structure humming with applied physics. This same gravity-driven overflow logic governs rice paddy irrigation systems, aqueduct networks, and tiered water features in public fountains. The Champagne Pyramid is a miniature model of hydraulic engineering principles dating back millennia. Getting the physics wrong is expensive. A standard champagne fountain for 200 guests requires roughly 30 to 32 bottles of champagne. At premium event pricing, a failed cascade from an aggressive pour wastes thousands of dollars in foam and spillage. Hard numbers. Mid-range event champagne runs $150 to $500 per bottle wholesale. 40 bottles puts the liquid cost alone between $1,200 and $2,000 before venue, glassware, or staff. One careless pour that triggers foam collapse can waste a quarter of that in under 10 seconds. Which raises a question nobody thinks to ask. Is there a maximum size for a champagne fountain? How tall can the pyramid grow before physics, not budget, becomes the limiting factor? The practical ceiling comes down to glass compressive strength. According to glassware stress testing published by the European Container Glass Federation, standard soda-lime flutes, the type used at most events, begin showing stem microfractures under concentrated loads approaching 15 kilograms. A 7-tier pyramid, with its 28 glasses plus liquid, concentrates load at the 4 base corners, well beyond that threshold. Record-breaking fountains solve this directly. In 2008, the Weinigem shopping center in Belgium set a Guinness World Record using a 56-tier pyramid of over 43,000 glasses, achieved by mounting the structure on a rigid steel scaffold rather than relying on glass-to-glass contact for load transfer. Physics problem, engineering solution. The Champagne fountain is simultaneously a gravity engine, a fluid dynamics demonstration, a structural engineering challenge, and a kinetic energy management problem, all disguised as a party trick behind a tuxedo and a smile. Deanna Cowan, known as Physics Girl, built an entire YouTube channel demonstrating that party tricks and physics experiments are the same thing, wearing different outfits. The Champagne fountain is exactly that kind of elegant, accessible demonstration. Humans learn physics best when stakes are visible and consequences are immediate. The Champagne fountain originated in the 17th century in England and evolved over time, gaining popularity in the 1920s, making it one of the longest-running physics demonstrations in party history. Back on that Monaco rooftop, Max tilts the bottle slowly, pours against the glass wall, and waits. The top flute fills. The overflow begins. The cascade descends. 16 glasses. 0 spills. One very satisfied physicist in a silk robe. Here's a surprising parallel. Wealth managers use similar overflow logic when advising ultra-high net worth clients. Rather than selling assets and triggering tax events, clients borrow against investment portfolios, letting value accumulate to a threshold before it cascades into liquidity. The glass fills. You borrow against the rim before it spills. Same physics, different currency. Next time you pour anything into anything, ask what's actually controlling that flow, because the answer is never random. It's always physics, always gravity, and always more precise than it looks from the outside.